Okay, let's move on to the second classification by engineering behavior, which is the Unified Soil Classification System, or the USCS. So from this one, the original form of the system was proposed by Casagrande in 1942 for the use in the airfield construction work undertaken by the Army Corps of Engineers during the World War II. So for this USCS, or the Unified Soil Classification System, this was classified into two broad categories. We have coarse-grained soil that are gravelly and sandy in nature, with less than 50% passing through the number 200 sheave. So you make use of the symbol which is G or S, or you can have G, which stands for gravel or gravelly soil, and S for sand or sandy soil. So the second category is fine-grained soil. This is 50% or more passing through the number 200 sheave. So the group symbol starts with M, which stands for inorganic silt, C for organic clay, and O for organic silts and clay. So we also use PT for peat, muck, and highly organic soil. So basically for the USCS, or the Unified Soil Classification System, you have the coarse-grained soil and the fine-grained soil. So other symbols that are used for the USCS, we have W to represent well-graded, P for poorly graded, L for low plasticity, and H for high plasticity. Take note for L, low plasticity, the liquid limit is less than 50. H, you have high plasticity, the liquid limit is more than 50. So for this, for the proper classification according to the system, some of the following information must be known. So you have the percent of gravel, you have to know the percent of sand, you have to know the percent of silt and clay, the uniformity coefficient, and the coefficient of gradation, the liquid limit and plasticity index of the portion of soil passing the number 40 sheave. So this is the table which illustrates the Unified Soil Classification System based on the material passing on 76.2 mm sheave. So of course you have two categories, the coarse-grained soil, which is passing percentage is less than on the number 200 sheave, and you have the fine-grained soil, the passing percentage on the number 200 sheave is more than 50%. So we have here, of course, the plasticity chart, which we have illustrated and discussed a while ago in our previous discussion. So you have here the presence of the graph of the liquid limit versus the plasticity index. So basically the group symbol for coarse-grained gravelly soil are, we have this group symbol that is being used. So similarly, group symbols for fine-grained soil, you also have the symbol that are used to identify for fine-grained soil. So based on the ESTM designation, created an elaborate system to assign group names to soil. So you have here some of the summarized names for USCS classification system. You have the fine fraction, you have the coarse fraction, you have the gravel fraction, and the sand fraction. Of course, passing percentage for this, for the fine fraction, is percent passing on the number 200 sheave, coarse fraction, percent retained on the number 200 sheave, and gravel fraction, percent retained on the number 4 sheave, and sand fraction, percent retained on the number 200 sheave minus the percent retained on number 4 sheave. So after the USCS, after you have discussed the classification by engineering behavior, the AASHTO and the USCS, we move on now to particle size distribution curve. This particle size distribution curve can be obtained through sheave analysis. So in the sheave analysis, it consists of shaking the soil sample through a set of sheaves that have progressively smaller openings. So for the sheave analysis, you make use of all the number sizes of the number of all the number of sheaves that we're going to use for our particle size distribution curve. So we make use all the openings of our sheave number. So it starts from, we have 4 up to number 30. So we have here the opening or the diameter for 4 up to 30, and for 35 up to 270. These are the diameter for our US standard sheave sizes. So to conduct sheave analysis, the soil is first oven dry. Of course, we have to oven dry to perform the sheave analysis. We have to oven dry first our soil sample. Then all the lumps must be broken into small particles. Then the soil is then shaken through. Then after we have oven dried, after we have broken the lumps into small particles on our soil sample, we're going to place that on a stack of sheave with the openings of decreasing sizes from the bottom to top. So meaning to say, we're going to use a pan is placed below the stack. After you have placed the soil on top of the first sheave number, you're going to place that on a vibrator. So after 10 minutes, get the stack of sheave number, then you identify the mass retained on every pan. Then afterwards, you can tabulate that one. So based on the tabulation, you can have your tabulation by identifying the number of sheave, then the openings, on the second column, then the third column, the mass retained per pan, on the fourth column, the cumulative mass, and on the fifth column, the percent passing. So the portions retained on each sheave are collected separately and oven dried before the mass retained on each sheave is measured. So you just have to follow these steps on how to identify our percent finer. So our F represents our percent finer. So what's the use of the particle size distribution curve? It is used to determine the 4 parameters for a given soil. So the 4 parameters that can be obtained through the particle size distribution curve are the effective size D10. This is the diameter of the particle size distribution curve corresponding to 10% finer. Then you have the uniformity coefficient C sub U. This is defined by this expression D60 over D10, meaning to say this is the diameter of the 60% passing, 60% finer rather, and you have the coefficient of gradation CC. It is defined by this expression. D30 refers to the diameter corresponding to 30% finer. Then of course the last one is the sorting coefficient. This is expressed in this manner. D75 is the diameter of the 75% finer. D25 is the diameter of the 25% finer. So the sorting coefficient is not frequently used as a parameter by geotechnical engineers. So the percentage of gravel, sand, silt, and clay size particles present in a soil can be obtained from a particle size distribution curve. So as an example, we'll use the particle size distribution curve shown in the figure to determine the gravel, sand, silt, and clay particles as shown. So that is according to the USCS, or the Unified Soil Classification System. So for this one, we have here the different types of particle size distribution curve. So for the particle size distribution curve, you just have to graph along the x-axis the particle size diameter, then along the y-axis the percent finer. How to obtain this one? So that can be obtained through you can tabulate actually based on the mass retained after you shake the soil on the pan that you have, the stack of sheave number that you have placed on a vibrator, on a shaker, that you have placed on a shaker rather. So the stack of pan wherein there is a soil sample on top should be placed on a shaker for 10 minutes. Then after 10 minutes, you have to get that one. Then you just quantify the mass of the soil sample on each sheave that was retained. So to apply that one, to illustrate, let's have an example. The following are the results of a sheave analysis So you have here sheave number 4 up to 200, and of course up to the pan. So the mass of soil retained on each sheave, so this was the mass of the soil that was retained on each sheave after shaking the stack of pan. So you're going to have calculation and plot the grain size distribution curve. You have to determine the D10, D30, and D60 from the grain size distribution curve. Then compute for the uniformity coefficient and coefficient of gradation. So to start with, you have to tabulate. So you copy the given, then identify the opening or the diameter for each sheave number. Then you copy the given, which has the mass retained on each sheave. Then compute for the cumulative mass retained above each sheave. So to compute that one, you start with a 0 on the number for sheave. Then 0 plus 21, this is 21.6. 21.6 plus 49.5, this is 71.4. Add to this, 173.7. You add to this, 262.8. You add this one to this, there is 358.4. You add this one to this, you give us 418.4. So try to sum up. And then you are going to add 418 to 312, so you give us 450. So that is the summation of M. Then afterwards, after you have the cumulative mass, get the percent finer for this. Percent finer is you're going to have summation of M minus column 4 times column 4 all over summation of M times 100. So you simply have to follow this equation. Column 4, summation of M is this one. Column 4 is this. Then after you have subtracted and divide, you multiply by 100. You give the value for the percent finer. So that's how you present our tables. Then afterwards, once you have that given, you try to plot the particle size, the diameter along X. You have to place the diameter along X, then pair that with the percent finer. So meaning to say the percent finer that correspond to the particle diameter. So the particle diameter is this one. This is the diameter that you're going to plot along x-axis. Then along y-axis is the percent finer. So each diameter has its corresponding percent finer. You plot this along y-axis. So this one you plot along x-axis. This one you plot along y-axis. Then afterwards, you simply have to get the once you have plotted that one, you try to connect the dots, you connect the points, and this is now our particle size distribution curve. So once you have plotted your particle distribution curve, you can now solve for the other unknowns, which is the diameter of a percent finer.